Lecture 4. Matrices and matrix operations. Matrices are fundamental concept in linear algebra and are essential tools in data science. Understanding matrices and their operations enables us to solve systems of linear equations, perform transformations, and manipulate large datasets efficiently. Section 1. Definition and types of matrices. In this section, we will define what a matrix is and explore the different types of matrices. Some of you may think that explanation of various matrices are boring, but it is not true in this lecture. I will give you some insights of how these various matrices enable us to do data analytics more efficiently. A matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. The elements of a matrix are enclosed in square brackets or parentheses and are organized in a grid-like format. Matrices are used to represent and manipulate data in a structured way, making them useful for computations and various operations in linear algebra. Mathematically, a matrix is defined as a collection of numbers arranged in a fixed number of rows and columns. If a matrix has m rows and n columns, it is called an m by n matrix. The individual numbers in a matrix are called elements or entries. This is an example of 2 by 3 matrix named matrix A. It has 2 rows and 3 columns. Here, A11, A12, A13, A21, A22, and A23 are the elements of the matrix A. The element Aij represents the entry in the ith row and jth column. These are basic types of matrices. Row matrix is a matrix with single row. It is the same as a row vector. This example, matrix A is a 1 by 3 row matrix. Column matrix is a matrix with single column. It is the same as column vector. This example, matrix B is a 3 by 1 column matrix. Square matrix is a matrix with the same number of rows and columns. This example, matrix C is a 2 by 2 square matrix. It's called a square matrix. Other than these 3 types, there are various types of matrices. Understanding various types of matrices helps us choose the right techniques for specific problems in data science. So, let's see other types of matrices. First, let's focus on zero matrix. A zero matrix, also called null matrix, is a matrix in which all elements are zero. Zero matrices are typically represented by O. This is an example of 2 by 2 zero matrix. Adding a zero matrix to any matrix does not change the original matrix. An identity matrix is a square matrix with ones on the diagonal and zeros elsewhere. That is, all elements from the top left to the bottom right are ones. Other elements are all zeros. Identity matrices are typically represented by I. This is an example of 3 by 3 identity matrix. Multiplying a matrix by the identity matrix does not change the original matrix. It is similar to multiplying a number by 1. A diagonal matrix is a square matrix in which all the off-diagonal elements are zero, meaning only the diagonal can be non-zero. This matrix, D, is an example of 3 by 3 diagonal matrix. Diagonal matrices are useful for scaling operations. As an example, let's consider the following 2 by 2 diagonal matrix and another 2 by 2 matrix A. Now, if we multiply this diagonal matrix by a matrix A, each row and column of matrix A is scaled by the diagonal elements of matrix D. Specifically, A's first row is multiplied by 2 and the second row by 3. In this way, diagonal matrices enable simple scaling operations, simplifying complex matrix computations. A scalar matrix is a diagonal matrix in which all the diagonal elements are equal. This matrix S is an example of 3 by 3 scalar matrix. Scalar matrices are a special case of diagonal matrices and are used to scale vectors and matrices uniformly. As an example, let's consider this 2 by 2 scalar matrix, where all diagonal elements are equal, and consider this 2 by 2 matrix A. If we multiply the scalar matrix by a matrix A, each element of a matrix A is multiplied by 4. It is because the scalar matrix has the same diagonal value, 4 in this case, in all its diagonal entries. In this way, scalar matrices are useful for uniformly scaling all elements of another matrix. Next, let's see what upper and lower triangular matrix are. An upper triangular matrix is a square matrix in which all elements below the main diagonal are 0. This matrix U is an example of 3 by 3 upper triangular matrix. A lower triangular matrix is a square matrix in which all elements above the main diagonal are 0. This matrix L is an example of 3 by 3 lower triangular matrix. Upper triangular matrices and lower triangular matrices are special cases of square matrices and are used to solve systems of linear equations and in certain matrix factorizations. Let's see an example of how this upper triangular matrix is useful to solve systems of linear equations. Consider these systems of linear equation. Usually, you will solve this system in this way. This system can be represented as a matrix equation. The left matrix is the upper triangular matrix U. Here, we can find the inverse matrix of matrix U. Inverse matrix is a matrix that, when multiplied with its original matrix, results in the identity matrix. So, by multiplying both sides of the equation from the left by the inverse of U, we can easily find a solution to the equation. Lower triangular matrices can be applied in similar way. The application to matrix factorization will be covered in later lectures. A symmetric matrix is a square matrix that is equal to its transpose. Transpose a matrix means flipping it over its diagonal, swapping its rows with columns. This matrix M is an example of 3 by 3 symmetric matrix. Imagine you have 3 points on a two-dimensional plane, point A, B, and C. We want to calculate the distances between these points. We can create a distance matrix where each element represents the distance between these points. DAB is the distance between point A and point B. DAC is the distance between point A and point C, and so on. Since the distance from A to B is the same as from B to A, DAB equals DBA. The same applies to other pairs. So, this matrix is a symmetric matrix. And so, we need to compute distances for only half of these elements. In data science, we often use distance between data points to quantify the similarities between data points. This method is useful in cluster analysis, where we want to group similar data points together. By using symmetry, we save computational resources and storage because we only need to compute and store one half of the matrix. An orthogonal matrix is a square matrix whose rows and columns are orthogonal to each other, and each row and column is a unit vector. Specifically, for a matrix A to be orthogonal, it must satisfy this condition. That is, the transpose of A multiplied by A is equal to A multiplied by its transpose, and both are equal to the identity matrix. This matrix A is an example of an orthogonal matrix. Since the definition of orthogonal matrix is complex, let's focus on the first component of the definition. Let's visualize the first row vector and the second row vector of this matrix A. We can see these vectors are orthogonal to each other. Next, let's visualize the first column vector and the second column vector. Again, these vectors are orthogonal to each other. Now we can see the matrix A meets the requirement of being an orthogonal matrix. Next, let's focus on the second component of the definition. It says each row vector and each column vector should be a unit vector. A unit vector is a vector whose length equals 1. So, let's compute the length of each row vector. We can compute the length of a vector using a Pythagorean theorem in this way. We can see that both row vectors have a length of 1. The same process applies to the columns. Since each row and column has a length of 1, they are all unit vectors. So, this matrix A meets the second requirement of being an orthogonal matrix. Another condition for a matrix to be an orthogonal matrix is must satisfy this condition. That is, the transpose of A multiplied by A is equal to A multiplied by its transpose, and both are equal to the identity matrix. For this matrix A, this equation holds. So, this matrix satisfies this condition. Let's see how orthogonal matrices are applied in data analytics. As an example, consider a case we want to rotate data points in two-dimensional space. Such rotations sometimes help us understand the underlying structure or patterns better. Using orthogonal matrices, we can rotate a vector while preserving its length. As an example, let's take vector V, an orthogonal matrix R. If we multiply these in this way, we get this vector. By visualizing, we can see that this multiplication rotates the vector V 90 degrees counterclockwise, while keeping the original length. Matrices are applied in data science and machine learning for representing and manipulating data. By understanding various types of matrices, we can obtain robust understanding of various problems, such as data representation, data transformation, efficient computation, and so on. In the next section, We will delve into matrix operations such as addition and multiplication to further explore how matrices are used in practical applications. Thank you for watching. Please thumbs up and subscribe to my channel.